And of course, the main point is that to get to this, Riccati-type equation or the viscous Hamilton-Jacobi type equation, and you have the nonlinear term on the right-hand side here, and it's the derivative u to the q. And for this, we can deal with all p, okay? But there are some restrictions on q here. We can also do it for some. We can also do it for some q less than 1 as well, but the p cannot be close to 1 in that case. Okay, I'll tell you. I want to make a remark on the principal operator. I mentioned about this earlier already. So we can work with the Laplacian, but we can also work with a little bit more general quasi-linear operator. But there is some distinction between the integral estimate and the pointwise estimate. For the integral estimate, we need that the A be VMO, V continuous or it satisfies certain VMO condition in the X variable here. But for pointwise bound, we need stronger. We need like Holder or Dini condition on the X variable, right? But I will, for the talk, I will just mention the Laplacian. And because we're trying to do it up to the boundary, so we need assumption on the domain. Okay, without that, there will be some problems. And the assumption is that for this talk, you can think the domain is good in the sense that it's in the class C1. The class C1 will be okay. But you can also extend it to the so-called Reinberg flat domain and so on. And this has been explained by the talk of Professor Buon, so I don't want to mention it here. Okay. So the first result is about integral bound. We call it Nguyen-Cong type bound. Okay, and this was done in 2014, and recently it was extended to the lower range of B, and it was done in 90. Okay, so suppose that mu is a finite measure in the domain, and the P is bigger than 3/2. Okay, Q bigger than 0. Okay, then for any weight in the A infinity class and any renormalized solution to this Laplace equation with right-hand side measure mu, we have the bound. Okay, the weighted bound W on the left-hand side. The same weight on both sides, but then you have the derivative of u to the q, and then you have the fractional maximal function of mu to the q over b minus 1. All right, and this is Lobo. Okay, this is Lobo. So, well, it's of course, I explained this very close to pointwise bound, but it's not white. And so let's see, yeah. So this is true for any renormalized solution. Now we have another result that has been submitted for some time. And we can do it even when b near 1, okay, up to 1, okay? But we cannot do it for all q bigger than 0. We can only do it for q bigger than 2 minus b. And the way is no longer in the A infinity class. It's A sub q over 2 minus b. In particular, it works if the weight is in A1. And that will be enough for our application. Okay? So there's some problem when b less than 3/2 in here. And of course, I should say that there is some subtle point here. We have this bound, but the statement was this: there is a solution that satisfies this bound. In particular, if you know the uniqueness, of this problem, then you have the bound for any solution. But in general, because we don't even know the uniqueness of this problem, so what we can do is that we say, okay, in this situation, when b is small, we find a solution with this bound. Of course, if the mu is good, say mu is if mu doesn't see the set of 0 p capacity, or if mu is a 1 function, then of course you have uniqueness. Okay, this is well known, and then of course the estimate is true for any solution, but the correct statement for us should be that there is a solution with this bound. All right, and the key, of course, to this one is the so-called comparison estimates. Okay, so what is that? You look at this is the original equation that you want to estimate, right? And then you localize it. You look at a ball inside your domain, and then you look at the function w. W equal to u on the boundary of the ball, and the w solve the corresponding Laplace equation with, w is a b harmonic function in the ball, okay? And then you try to see what is the difference between u and w, all right? And the estimate is that, so say for b less than 2 minus 1 over n, the estimate is, and then for gamma, this is for gamma less than this power. I mean, this is the theoretical power, because for any equation which measure that the solution will always in L gamma when gamma less than this one. Then the difference here is controlled by the measure for this original equation plus some nonlinear expression here. Okay. The gamma 0, you have both gamma 0 on both sides here. Okay, the history of this, okay, I should say that the first contribution to this should be in the paper mentioned in 2007, where you can find this in the case when b bigger than 2. And in that case, when say when b bigger than 2, you don't even have this term. You don't even have this term, okay? And then when b between 2 and 2 minus 1 over n, I found that result in the paper mentioned in Louisiana in 11 and JFA paper. And this is where you see this little, you know, A1 norm here. So in their situation, they work with gamma 0 to be equal to 1. Okay, because in that case, when b bigger than 2 minus 1 over n, this power will be bigger than 1. Okay, and of course, we were trying to do it be bigger than, less than this one. So what he knew is only when b less than this 2 minus 1 over n. But the idea was in the paper mentioned in 2007, right? So of course, the case when b less than this is still open. As I mentioned it earlier, there is some partial result in this case. Okay, but in this case, what we can do is that we have to put the gamma here, could be anything small, but we get some result that we have to put gamma 0 equal to 2 minus b in this case, okay? So there are results, but the gamma 0 has to be 2 minus b in this case. And because of that, our result has some problem with, we have to ask q bigger than 2 minus b in here, okay? So there are comparison estimate when b smaller than 3/2 here, but then there is the power 2 minus b here. It's not the gamma 0 anymore. So that's a technical problem that we cannot, completely overcome. Okay. And now let me tell you how. Maybe I just tell you like a heuristic way. It's not like a correct way to say it sometimes, but that will give you the idea how you would prove something like this. If you think it's in the point of view of harmonic analysis. To prove something like this, you're gonna say interpolate. You try to interpolate, okay? The case say let's look at a situation where W is 1, okay? Where W is 1, you try to interpolate. Say it's easy to see that it's true for a small q. Say q equal to q sub 0. It's always true, and you don't even need the fractional maximal function. You can just need the total mass for the measure. Okay, so when q small, you can just use the total mass and you get about. You don't even need the fractional maximal function and so on. Now, then you interpolate between q, LQ sub 0 for small q sub 0 and then L infinity. Now, I say L infinity is not true because you don't have this bar at the level L infinity. Well, however, you have the L infinity bar for the harmonic function, for the p harmonic function. Okay, you have even C1 alpha. Okay, but you don't really need the full force of C1 alpha here. You just need L infinity norm. Okay, and then so you try to interpolate that, but then you have only the L infinity norm for the homogeneous equation. So you really need to know the information between the difference of W and U, and there you need the different estimates here. Okay, I think the idea of this go back. I don't know who. Of course, Caffarelli have some sort of idea like this, and then later on there are the work of Iwanya. You can see something like this as well. But the first time where you have the low, below critical exponent for a different estimate is that in this 2000 paper, okay, 2007 paper. All right, so let me explain the difficulty when B gets small, okay? So why is this?
Can I make one remark?
Yes, yes.
Only one remark, yeah.
Yeah.
On the history of this estimate. Okay, I actually first obtained this estimate in the range P larger than 2, and then with Frank for P larger than 2 minus 1 over n, where this additional term appears.
Mm-hmm.
And then this was first used to get level sets estimates. That is, you can estimate the gradient,
Mm-hmm.
the level set of the maximal operator of the gradient with the fractional maximal operator of,
Mm-hmm.
the mu. So this approach was first cooked up to estimate the gradient with the maximal operator, or the fractional maximal operator of the right-hand side. And then the potential estimates came after. So they first came this maximal operator and then the potential as, let's say, a more general thing.
Yeah, I think I forgot that the journal for that paper.
No, it's Mathematischen Allen. It's a journal. It's a paper in Mathematischen Allen where I have that you can bound the gradient with the fractional operator of the mu for P larger than 2, I guess, in that paper.
Okay.
P larger than 2 in that paper. But then, of course, I didn't put these weights, these Magenhaupt weights.
So you do have this kind of different estimates on that paper.
Yeah. But for P larger than 2, then these allowed me to use the fractional maximal operator to bound the norm with the fractional maximal operator of the right-hand side. And then this was and then later on came for P less than 2, but it was not written there.
Okay.
So first the fractional maximal operators and then the potentials. So it's a bit of reverse of the story. In fact, the idea of getting these potential estimates came from the fact that I was first using fractional operators and then
yes, I am aware of that.
From the pointwise to the pointwise things. This is a very nice extension. In fact, it's a very non-trivial fact. I mean, this is.
You do locally inside, and what I do here.
Yeah. Then you did it at the boundary, and but this is a very nice fact with this range of parameters, which was certainly very non-trivial, and yeah.
Thank you. So let me explain a little bit about the difficulty when B gets small. Okay. So if you look at the fundamental solution to the B-Laplace equation, this is given by this this negative power, say B less than n. Then of course the derivative is in the Lorentz space like this. So if you want the derivative to be locally in L1, then you need of course P bigger than 2 minus 1 over n. So when of course then P less than that, the derivative will no longer be in L1, and this prevents us from using the Sobolev inequality in the traditional argument. By that I mean the argument of Minzoni and so on. Okay, so you cannot apply the Sobolev inequality there, and because if you stay below this, if our situation is below this. However, there is a very important observation by Quoc-Hung that even though this thing in L1, but if you multiply by v to negative power, it's actually in L1, and you can calculate exactly what power you need. And this means that if you raise v to certain small power, then that function v is going to be in L1. I mean the derivative function with v some power delta, v to power some, the derivative is going to be in L1, and you can apply Sobolev in that situation. And then in the calculation, you end up with something like perhaps in here. Okay, so that I mean the explanation. Short explanation. All right. So now I go to the point the radiant estimates. Okay, and let me mention the estimate for the function first. I did it. I mentioned this yesterday already, but to put it in perspective, I should mention it now. Like if you just want to estimate for the function, and this is the fundamental result due to Kibalainen and Mali that you can control. Two-sided the function by the work potential. All right. And by the way, someone asked me about the Wiener criterion yesterday. I mentioned the work of Kibalainen and Mali and Labutin, but I forgot to mention the work of course, Maza in the 70s, where he was the first to prove that the divergence of Wiener integral gives you the sufficient condition for regular points at the boundary. And then the paper here, this paper provide you show that that's actually also necessary. Okay. All right. So now now let's talk about the situation when you try to get point white bound on the gradient. Okay. So of course the first result due to Duza-Minjuni 2010, and then their result Uzi-Minjuni, the Alma paper in 2013. So it deals with a solution to the P Laplace equation with measure data mu and say P bigger than 2 minus 1 over n. Then you can control the derivative pointwise by this potential to the power 1 over P minus 1, and then plus some term here. Of course, this term is unavoidable because you work in a local situation. Now, what is this? This is actually a linear potential. It's not nonlinear, okay? It's a linear potential. It's a real potential order 1, but there's a power outside, okay? That's one thing. And then historically, the KB equal to 2 was done first by Minjuni in 2011. And then there's also the K when P bigger than 2 by Duza and Minjuni. In that case, the 1 over minus P, 1 over P minus 1 were inside its interval. So it's a work potential in that paper. And you can see that when P bigger than 2, if you can take the 1 over P minus 1 outside, you get a smaller quantity. And that in some sense, this ARMA paper gives very sharp improvement on this, American Journal of Math paper. All right. So in this range, you have linear potential estimates. Okay. And then the implication of this has been explained by Minjuni already. So basically, it's if you want the L infinity, I mean, you talk about like the Lorentz N1, then this gives you the estimate that is independent of P and so on and so forth. Okay. All right. So now let's talk about the K when P less than 2 minus 1 over n, but it's still bigger than 3/2 here. So we get a similar bar, but we need to use the work potential in this case. Okay, we have the power gamma 0 inside this one-dimensional integral here. All right, and the gamma is it's a small number. Okay, you want it to be large, of course. You want it to be large. You want it to be, but it can only go to P minus 1 n over n minus 1. This is the theoretical exponent. And yeah, so in general, gamma 0 here is less than 1. Okay, so this is different with the estimate that I mentioned earlier, and you want it to be large, right? Because of this easy to check fact that whenever gamma 1 is larger than gamma 2, then this one-dimensional integral is less than this one-dimensional integral. Okay, but this is the best we can do. We can go up to this power. All right, so again, let me mention a little bit on how do you prove something like this? Okay, of course, I can only say it at a heuristic level. So let's see how. Okay. So imagine this: you want to bound something like this, right? If you think like point white bound like L infinity bound, okay, but of course point white bound is not quite the same as L infinity bound. But if you think it that way, you would do this. You try to interpolate between say LP and C alpha, right? You need because you want to need the estimate at L infinity level. You need something that's better than L infinity, so it's going to be C alpha. So you try to interpolate between say LP, say LQ, and then C alpha, okay? And then the same, then as I mentioned earlier, you don't really have C alpha here. You have only C alpha for the homogeneous problem. So you try to bring in the different estimate, and that is what we need earlier. And then another thing that's very important in this is that even if you know C alpha estimate, but you need a C alpha estimate in a very, very sharp quantitative way, okay? So so now that's it by that. So now I want to tell you something that I call sharp quantitative C alpha estimate. So you look at a doubly, which is a solution to the homogeneous problem, and then you want to estimate, you want to find C1 alpha bound. Of course, this is well known. this is a classical result that you do have C1 alpha estimates here, and this is due to many people. John Lewis, Di Benedetto, Stonsdorp, Evan, and many others. Okay, this is classical. You can control the Holder the Holder norm of the derivative by just the L1 norm of the function of the derivative of the radian of the function. Okay, and then but this bow is not very useful for us. Okay, but then later on, Duja and Minier recognize this bow. Okay, so if you remember the equivalence of Campanato space and Holder space, then pretty much the two things are here are equivalent. Okay, but what you gain in the second bow here is that you can in the second in the right hand side here, you can put the mean oscillation, not just L1 norm, but you can put the mean oscillation. Okay, this is a very important observation, and it doesn't imply, this power doesn't imply this. So basically in that 2011 paper, Duza and Minjane have to redo this. They have to rewrite everything and they to get to this point, okay, because I feel like there's nothing available for this. So they have to really do it, even though the C1 alpha estimate has been known for some time. And but it's still, for this situation, you still deal with the L1 level, okay? But for us, we have to go down. We have to go like some L gamma 0 where gamma 0 less than 1. So how do you quantify this? So for us, we have to deal with a nonlinear vector field, okay? So you take, this is true for any p bigger than 1. You take a q, say between 1 and p plus 1, and then you look at the nonlinear vector field of this type. So, the absolute, the magnitude of this would be q minus 1, okay? So that means q minus 1 could be near 0, okay? So there is a constant C0 such that this expression is, if you replace C with the derivative of the solution to the homogeneous problem, then it's basically it's C alpha. But the C alpha norm can be expressed in a very symmetric way, okay? In the sense that the left-hand side and the right-hand side just look the same, except that on the radii here are not the same, but they look pretty much the same, okay? And you gain some power alpha here, okay? And I should mention that, of course, this is not completely new. In the case when Q equal to P, it was, we found this in the paper of Dinning, Kaplicki, Schwartz-Zacher, where they show the BMO estimate for the derivative in the K when P less than 2, and I think it's very close to what we do here, and we learn also something from this paper. For P bigger than 2, this kind of nonlinear vector field appear in the work of course, Duza and Minjane in the K when Q equal P plus 2 over 2. Okay, so the Q and in those papers are always bigger than 2, okay? But for us, we apply it with Q near 1, okay? And so we have to do it for us, okay, for our purpose. And in doing this, we have to use a lot of stuff, okay? So I think we learn a lot from the paper of Asabi and Fusco, and also Jaquinta Monica. If you want to read about elliptic reality, I think for the B Laplace, I think those papers are very, very good read. You can find a lot of tricks on, how to apply the Joachim-Nacht measure, how to apply Hartnacht, very interesting paper. And we learned a lot from the papers. And eventually we showed this. And as mentioned, that the importance of this is that this expression is quantified in a very, very sharp way, in the sense that both sides have the same structure, and this allows us to apply an iteration process. Okay, when you iterate, you don't lose anything, and then the power alpha will help you to iterate, and eventually you get the C1, the polar estimate. And of course, this idea go back again to the work of Duza and Minjane. Okay, and if you don't have the mean on the right hand side, you cannot do it. All right. So let's be now. So that's what the polar estimate, but it's for the local one. Okay. Let me mention now the global one. Again, when P is less than 2 minus 1 over n, and you look at the solution. Now I assume that the domain is C1 alpha, okay? C1 alpha domain. U is a renormalized solution to this problem with 0 boundary condition. Then we get the following result. For any small epsilon, okay, any small epsilon, okay, and any x inside the domain, we can control the derivative low up to the boundary for any point x. Now, this one-dimensional integral, you integrate from 0 to 2 times the diameter of your domain. And then you have the same potential, but then you lose something here you know, this is a negative power. You wish to have epsilon to be 0, right? This will go back to the Rin function estimate up to the boundary of Ruther, Wissmann, and so on. But we lose something here. But we work with C1 domain only, of course. You wouldn't expect this to be true for. I mean, you shouldn't expect this to true for epsilon equal to 0 if you work only with C1 domain. By the way, we don't even know how to do it for Randolph flat domain. We can do it for Lipschitz domain with small Lipschitz constant, but we cannot do it with Randolph flat domain here, okay? And of course, the hope is that you say that this should be true for C1 alpha domain, but we don't know how to do it, okay? C1 alpha domain. The reason is that we don't have this kind of estimate up to the boundary for now. There are C1 alpha estimate due to I forgot I forgot the name. Lieberman, right? Thank you. Right, but his estimate is you still need you cannot subtract the mean here, and I don't know. We don't know how to deal with that. And if you look at the paper there, the estimate is really based on the technique of the fully nonlinear equation. So it's kind of different. I mean, something is going on at the boundary that we still don't completely understand. However, if your boundary is in your class C2, okay, then we are able to remove the epsilon. I mean, you can put epsilon to be 0 here, but we are still working on this. This will be joint work with Quoc-Hung and Agnick, okay. All right. So that's the story. Now let me go to the application part for the rectified equation. So now what is the capacity then? Okay, what is the capacity? It turns out that the capacity is still of order 1. Okay, it's an S capacity. So in other words, it's like S capacity here. The derivative is just 1, but the S will no longer just P. There is interaction between P and Q here, and it turns out it's Q over Q minus P plus 1. So this is the conjugate exponent of Q over P minus 1. This will be the intrinsic capacity associated to this equation. And let me recall that this is the 1S capacity. All right. So it's associated to the superlap space of order 1. And so of course you need a necessary condition first. And this is known this is known in the linear case, at least in the linear case, to the you can find it in the paper Hansen, Mazur, and Verbitsky. And this is known to Igor Verbitsky, okay? And actually this kind of necessary condition were brought to me by Igor, okay? He knows this already. So for Q bigger than P minus 1, if there is a solution to this problem, say if Q is supported in the domain, then the manual mu has to be regular in the sense that it is controlled by the capacity. And this is the capacity. This is the capacity, and this is Q over Q minus P plus 1. This is true for any convection scale in the domain. Now the question is, can you go back? Okay, so if you assume this with small c1, can you solve the equation? And that is what I'm trying to do. So, so we can do this for all p. Essentially, we can do it for all p and for all q bigger than or equal to 1. Okay, so there exists a constant C0, so that if that capacity condition hold for C0, then you have a solution to this problem. And the derivative solution is in this space, okay? So it's in a similar, you can think the derivative to the QE like, behave like this measure here, okay? And I stated here for B less than 2 minus 1 over n, but it's also true for B bigger 2 minus 1 over n. It was done earlier in 2014. And of course, the KB equal to 2 is classical. This is due to Hans and Mazur and Verbitsky in 1994. And now let me mention the case, about the case when P, when P, now, yeah. So this is static for all P bigger than 1, but the K when P bigger than 1, I mean, there is this 3/2 power. So when P less than 3/2 power and the K when P bigger than 3/2 power, they are treated differently, not the same, because of that problem, okay? But because we have A1 estimates, so it's allowed us to do it. We don't really need point-wise estimates, but we need Q bigger than 1, okay? Because we need some convexity here. So let me mention some other cases and unsolved problems. So it does not cover the sublinear case, say Q less than 1, and when P bigger than this. But this has been settled with our recent result that we can do this, but we have to assume that mu is compactly supported. And we need, in this case, we need point-wise power. Okay, we need point-wise estimate for the gradient in this case. I mean, we need this estimates here. And because of this, we have to work with compactly supported measure. We cannot work with a finite measure. I mean, so there's still some problem to work on this. Okay. Now, the K when P less than 3/2 here and Q less than 1, this K is still unknown to us. Okay. This power is a critical one. Okay, this power is the critical. How do you know this is a critical one? Well, what you do is that you see that you set it equal to n. Okay, you set it equal to n. You solve this for Q, and this is exactly the power. Okay, I told you that. So how do you figure out criticality here? You just look at the capacity and you figure out. Okay, and of course, if Q is in this critical situation, then you can solve it. And I mean, there are many people working on this. Okay, I cannot list all here, but there are, I just want to mention the work of Renon, Mura, Oresta, 13, Besta, Mercado, Mura, Borzio in 2003, and so on. Okay. All right. Now, let me move to another situation. So basically, I found necessary and sufficient condition. The necessity part here is only for non-negative measure, and then the sufficiency part here for even sign measure, right? So of course, if you measure in non-negative, this gives you a necessary and sufficient condition, but again only in the best constant. But that doesn't mean that it so it doesn't mean that it's going to be sharp. Okay, at least when your measure is side changing. So what happened? How do you find sharp condition when your measure is side changing? Okay, so that's what I'm trying to do now. So when your measure is side changing, you think your measure is like a distribution. Okay, so you show that. Okay, so here's the result. So suppose that Q is bigger than P minus 1, and mu is a general distribution in the domain omega. So you look at this equation. Now your mu is a distribution, okay, a sign distribution in your domain, and then you want to look for a solution in this natural space, okay. So basically, I predetermine the space of solution, because what I mean from this existing result, this space is actually a natural space for the solution, and actually it's also a necessary space if you work with positive measure, okay. So that's why. So if the equation has a solution U in this class, okay, in this class, then one must have that the measure mu had to be in the form of a divergent of vector field F, and the vector field F also satisfies this capacitary condition. Okay, so this is the power Q. And because of the homogeneity, it's going to be the power Q over B minus 1. This kind of necessary condition, I mean, were found in the work of Mazur, J, and Verbitsky in a different situation. Okay, and but the argument also works here. So if you work with distribution distributional data here, and if you force to work in the framework of this of this space, I mean, this is some sort of Sobolev multiplier space, then you are forced that the measure, I mean, the data have to be in the divergent form of a vector field. And that vector field also satisfies some sort of capacitory condition here. Okay, and then you wish to go back. So suppose that my measure mu is in this form and my data F here satisfying this. Can you solve the equation? Well, it turns out it's very difficult. We can do it when Q bigger than or equal to P. I mean, this necessary condition is for all P bigger than 1, but to go back, we can only do it for Q bigger than or equal to P. Okay, so what we get is that for any C0 bigger than 0, I mean, for some C0 bigger than, there exists a C0 bigger than 0, so that if this condition holds for C less than C0, then we can find a solution to this problem. So the result of this direction was done first in the paper, Mengesa and me, but we work in the framework of Morey space. Okay, so the condition is stronger than this. And then we, in our recent paper, we can do it with the capacitory condition. And then there are work with arithmetic where we deal with the situation when P equal to Q. And there are also work J, Mazur, and Verbitsky in the KP equal to Q. The KP equal to Q is a very interesting case actually. In this case, you can transform it into, I mean, you can some sort of you call Hopf transformation. You can transform this into Schrodinger type equation. And then you don't work with the derivative anymore, you work with the function. Okay, so that was the idea, and of course this is known to other in the world, Mura and other people, but that approach was used by J, Mazur, and Verbitsky. But for us, we don't transform it into the Schrodinger equation. We work directly with the, in particular, we work with, in our arithmetic, we work directly with the Riccati type equation here. Okay, we try to obtain the gradient estimate directly. Now, I said that it is unknown here when Q less than P. And of course, this is intimately, okay, connected to the so-called Iwaniak conjecture, okay? Let me mention, I will mention about this later on. So now I give you an example that to show that this condition is actually sharper than this condition. Here you take the absolute value, I mean, you take the total mass here. When you take the absolute value, you really destroy the cancellation, the cell cancellation of your data. So the example is this. So you can find this kind of example in the paper of myself and Mangesa, but you can also find it in the earlier work of Mazur and Verbitsky. So basically, you can look at some data that will oscillate very fast, okay, near the origin. Okay, so now if you treat this one as a sign measure, okay, then you try to calculate that condition. Okay, so you take the absolute value of your data, and then you realize that it doesn't satisfy that capacitory condition, because when you take the absolute value, you really destroy the cell cancellation. Now, if you apply this, then you're okay, because this data here, you can always write this as a divergent of a vector field F plus a good function. So that F is this function. And then you can see that this F actually satisfies this capacitory condition. And then the thing is, after you write out at a divergent of vector field, you don't destroy the cancellation here. And then you can apply it, you get the existence here. Okay, so that's the point of using divergent form structure here. Okay, and it's very natural that you have to work with divergent data here, because your equation is in divergent form, right? It's divergent form. Okay. Now, of course, so that's why I said that the study of this Riccati type equation with the distribution data here, datum here, has motivated the study of just this equation without the nonlinear term. And where in this study we look for weighted Caron-Zygmunt type estimate of this type. And for now, this is true. I mean, this estimate is known to hold when the weight is in the Munkenhood class A Q over P. Okay, when Q bigger than B. So you need Q bigger than B in this estimate. So it was done first done by myself, and of course the the K, of course, the case, let's look at the K, the simplest K is W equal to 1. And this is well known. Let's go back to the work of Iwaniak, and there are other work, Barao, Kafar and Lee, and then there are work of Kinunan and Zhu, Beun and Wang, and of course, this has been mentioned a lot in the work of Beun, many others, okay? But the first one who I mean, the first weighted estimate in my 2011 paper, because I want to, I try to get, at that time, actually, I did not know about polarized estimates, okay? So I did with divergent form here. So I found out that, okay, you don't really need a polarized estimate. And of course, you don't have really polarized estimate. You do have some sort of polarized estimate, but it's not useful, okay? So you need weighted estimates, and that you can think weighted estimate is some sort of a substitution for polarized estimate, and you need only A1 condition here. And I mentioned that the reason is that the nonlinear potential, if you raise to some power, it's actually in A1 class. Okay. Now, if you want to do this, and of course, if you want to do this with A1 weights here, of course, the K and Q equal to P. If your W is 1, this is just the energy estimate, okay? It's easy. But if your W is A1, A1 is not that trivial, okay? Not trivial. And but if you use some idea from Iwaniak or some idea from John Lewis' paper, you can do that, okay? This is the higher interactability situation. If you gain some higher interactability on a homogeneous equation, then you can do it with A1 for all A1 weights here. We don't know how to do it for Q equal to P minus epsilon for all A1 weights, okay? I want to mention that when W is 1, you can even put Q to be equal to P minus epsilon. And this, of course, this is the work of Iwaniak and John Lewis and so on. And the K, even when W equal to 1, okay, the K and Q less than B is still open. And this is essentially the conjecture of Iwaniak. And that's why we don't know how to do it when Q less than B, okay? So it's even this fundamental problem, there's still no, it's not known in this range. And this is what I call the Caron-Zygmunt-Time estimate, because if you look at the Laplace equation, this is the radon can be expressed as a singular and zero. Now there are work in the K and P equal to 2. In that case, you can take any AP way. I mean, if you add the AP, you can take AQ weights. Okay, of course, you would expect that the correct one is Q B minus 1, but still not known. Okay, and with that existent result, you can show that the singular set, I mean the removable set, is exactly the set with zero capacity. So after you know existence, then you can see that the necessary condition for removability is the condition that the capacity is 0. Now this is sharp because if we know the capacity is 0, you can always remove your you remove it. Okay, so if you have a compact set E with 0 capacity, then any solution to this problem in the domain omega minus E can be extended to a solution in the whole domain omega. Now, there are subtle thing here, and I should mention, say when U in the K when Q bigger than B, I really need that U is B superharmonic in the whole domain. The reason is that when Q bigger than B, this capacity is actually smaller than the P capacity. When it is smaller than the B capacity, then this, when it is 0, it doesn't mean that the B capacity is 0. So you cannot really remove B superharmonicity function, okay? So you cannot deal with the B superharmonic, I mean, you cannot remove B superharmonic in this situation. So in particular, when Q bigger than B, okay? Because the capacity is going to be smaller than the P capacity. But when Q bigger than equal to B, this capacity is going to be larger than the P capacity, and then you don't really need this condition. You just work with P superharmonic in omega minus E, and then you can always extend it, as I mentioned earlier. All right? So there's some technical thing here. And yeah. Okay, I think that's all I have to tell you. Thank you very much for your attention.